Okay, good morning, guys. Thank you for hanging around. Sorry for the delay. We've lost some time, so let me just get switched over here and get moving. All right. With that little bit of time lost and with the holiday this week and with the office hour lost to the hurricane stuff and everything that's been going on, we may not get through all of the material this week that I intended. But we're going to do our best. I do want to show you guys Taylor's theorem today because this is kind of the big payoff. After you look at all of the infinite series stuff that we've done, the kind of goal here is to get to a place where you can write a power series for just about any function. And that's what Taylor's theorem lets us do. So you think of everything that you've done since we started preparing for exam 2 up until now, this is sort of the crowning moment. This is the achievement. The other thing I wanted to do today, besides show you Taylor's theorem, of course, is just get a little bit more practice with the 11.9 problems that you guys have been handed this week. So I'm going to pop up the chat here. While I'm writing the kind of basic, we always do them things on the page, like the class and the day. If you would like to see any particular problems from the last homework set, feel free to go ahead and hit them in the chat. So this is MAC2312, section 001. That's the lecture for 11/13/20. The exam grades, of course, are up. I don't remember if your class had them on Monday or if you had to wait for Wednesday, but today, some more power series examples. These could come from 11.8 through 11.9. And then also the big deal is Taylor's theorem. All right. So Zach would like to see number 5 from last week's homework. Is there any other homework problems that you guys are just itching to see worked? Just for shits and giggles, can I see with the thumbs up react if you've gotten past number 5 in homework 10? I'm sorry, homework number 5 in homework 11, this week's homework. Can I get a thumbs up react if you've started this week's homework? Okay. Okay. That's useful information for me. Thank you. All right. Oh yeah, this is fun. So let me write it down and then I'll switch back to the doc cam. Cool, thank you, Zach. All right. So you guys remember the example with the logarithm that we did at the end of class last time? I think it was the natural log of 3 minus x. Our very first step was to use properties of the log. All right, remember with natural, we have a power series for ln 1 plus x that we can make use of, that we discovered by integrating a power series for 1 over 1 plus x. And when we got the power series for the natural log of 3 minus x, we did it by first factoring out the 3 and then using properties of logarithms and then taking our power series for 1 plus x and substituting something in. A similar first few steps here. My very first step would look like this. Remember, a logarithm of a ratio is the difference of the logarithms. Here I'm using this rule for logs. As regardless of the base. I start by using this rule. This fellow I have a power series for. This fellow I know how to cook up a power series for. So from here I would say now recall that the natural log of 1 plus x, this is something we have a known series for. And it was one of the series I put in a box in our lecture on Monday and said, we got to remember this forever and ever, along with its IOC. It was the sum from n equals 0 to infinity, negative 1 to the n over n plus 1 times x to the n plus 1. Everybody remember that? Now, if I swap this x for a negative x, then I'll get sigma n from 0 to infinity, negative 1 to the n over n plus 1 times negative x to the n plus 1. So these are the two series I'm going to have to combine. But first I want to simplify this a little. Oh, sorry, I left off an n here, negative 1 to the n. So these are the two series I'm going to have to combine. But first I want to simplify the lower series a little bit. Any questions about where the lower series here came from? I'm just taking the x in this series, which we discovered before, and replacing this x with a negative x to change this plus to a minus. And that just has the net effect of making the x in the power series negative. Now, that's the same as negative 1 to the n times x to the n. N plus 1. Negative 1 to the n plus 1 times x to the n plus 1. All right, this negative on the inside is the same as multiplying by negative 1. So this is negative 1 to the n plus 1 times x to the n plus 1. Everything else staying the same. And now this term and this term can talk to each other. They're being multiplied and they have the same base. So we can add the powers. Negative 1 to the n times negative 1 to the n plus 1 is negative 1 to the n plus 1, which is 2n plus 1. And since 2n plus 1 is always odd, negative 1 to the 2n plus 1 is just negative 1, which can come outside the series as a negative like that. Giving us this. So now, f of x, which is the natural log of 1 plus x, minus the natural log of 1 minus x, is this first series minus this second series. Okay. Maybe I'll put this one in parens also to help us see exactly what's going on. Here's the series for the first piece. Here's the series for the second piece. Now, of course, this minus a negative is going to become a plus. And this is what we get. Certainly, this is not written as a single power series yet. Oh, I need my x to the n plus 1 here, sorry. So before I can write this as a single power series, I need to see how these two are going to combine. And there's a bunch of ways to do that. I'll show you how to do it while staying within the sigma notation. First, remember the capital sigma obeys the same rules as a definite integral. So think of this as like integral from a to infinity of some shit plus integral a to infinity of some other shit. I could write that as a single sum, just like you could write that as a single integral, where the shit inside is added up. So this is negative 1 to the n over n plus 1, x to the n plus 1 plus 1 over n plus 1, x to the n plus 1, like this. Here I'm using the fact that sigma an plus or minus bn is the same as sigma an plus or minus sigma bn. As long as they're being summed over the same range. So I'm using this to take these two series and put them together into one series like this. I'm going from a statement like this to a statement like this. And now within these purple parentheses at the bottom, I have quite a bit that I can factor out. What's common in these parentheses? The x to the n plus 1 and a 1 over n plus 1. So I get sigma n equals 0 to infinity. I'll have a negative 1 to the n plus 1 times 1 over n plus 1 x to the n plus 1. So I've factored out an x to the n plus 1 from both of these expressions and a 1 over n plus 1. What's left from this piece is the negative 1 to the n. What's left from this piece is the 1. And you could write it like this. But if you think about what this guy does something interesting. When n is even, this is equal to 2. And when n is odd, this is equal to 0. Let's write out the first few terms of this series. So you could stop here. This is done. I want to be clear about that. This is done. But it's kind of opaque. It doesn't really help me see exactly what's going on. So if we wanted to get a better feel for what this series looks like, I would recommend writing out the first few terms. When n is 0, This is 1 plus 1 times 1 times x. That's 2x. When n is 1, this is negative 1 plus 1 times 1/2 x squared. That's 0x squared. 0, we could say 0 over 2 x squared. This being the 2. When n is 3, I'm sorry, n is 0, 1, 2. When n is 2, this is going to be 1 plus 1, which is 2. This is going to be 3. And this is going to be x cubed. All right, if you want to kind of think about it the same way, the 1 over n plus 1 was a 1 here. Help you see the patterns. Okay, so this is n equals 0, this is n equals 1, this is n equals 2. When n is equal to 3, this piece is going to be 0 again. This piece is going to be 4, and this piece is going to be x to the 4. When n is 4, this piece is going to be 2 again. This will be 5, and this will be x to the 5. When n is 5, this piece is going to be 0 again. This would be 6, this would be x to the 6, and then you'd have 2/7, x to the 7th, and so on. And what you'll notice is that every other term is 0. And the non-zero terms all have a 2 upstairs. So let me just rewrite these without the 0 terms. This is 2x plus 2/3 x cubed plus 2/5 x to the 5 plus 2/7 x to the 7. And I could rewrite this in sigma notation if I wanted to. Let's say we'll have it start at n equals 0. Clearly there's a factor of 2 here everywhere. Downstairs, this has a 1, 3, 5, 7. And the powers are also 1, 3, 5, 7. So if I'm going to rewrite this as a single sum, as clean as possible, it's going to look like that, which I think is much prettier than this. But it's very hard to see that this is equal to this without going through these steps of writing them out. And I mentioned back when we got to this stage, that you can combine them in the sigma notation to get this, and that's fine. But another option would have been to write them out, write both power series out long form at this step, and combine them into that final form that I just gave you there. So I'm going to put this back. Okay. And you guys can tell me if there's any part of this you want to look at more closely. Maybe I'll move this just like this so you can see the individual steps a little better. Zoom out a little bit. Like this. So what parts of this would we like to look at more closely? We want to look at the IOC. So to find the IOC, if we don't want to use any kind of tricks, any sort of observations about the two series we started with, we could just run the ratio test on this. Remember, this is always how the ratio test begins. So here that's going to be the limit as n goes to infinity, absolute value an plus 1 is 2 over 2 times n plus 1 times x to the 2n plus 1. There's an plus 1. And then I'll multiply by the reciprocal of an, which is 2n plus 1, son of a bitch, work, over 2x to the 2n plus 1 like this. Switch to this pen. All right. So this is lim n to infinity. I'm going to switch to a black pen here because that purple pen's dying. 2 times x to the 2 times n plus 1 is 2n plus 2, plus 1 is 2n plus 3 over 2n plus 3. And then over here I have 2n plus 1 over 2x to the 2n plus 1. And like we always do, we can put the kind of similar looking terms together. First I've got a 2 over 2, and then I've got x to the 2n plus 3 over x to the 2n plus 1. And then I've got 2n plus 1 over 2n plus 3. Two over 2 cancels, that's 1. X to the 2n plus 3 over x to the 2n plus 1 cancel to x squared. So I'll have lim n to infinity, absolute value of 1 times x squared times 2n plus 1 over 2n plus 3. I can pop out an absolute value of x squared. And then 2n plus 1 over 2n plus 3 is definitely always positive, so I can lose the absolute values there. What is the limit of this remaining piece here? Good, yeah, that's 1. So the limit L from the ratio test here comes out to the absolute value of x squared. Thus, L will be less than 1 if and only if the absolute value of x squared is less than 1, which is the same thing as saying the absolute value of x squared is less than 1, which is the same as saying take square roots on both sides, the absolute value of x is less than 1, which we can then expand. As -1 is less than x is less than 1. So my radius of convergence is definitely 1. The series is centered at 0, and I can walk to the right and to the left no more than 1. And I need to check the endpoints. When x is equal to 1, my series becomes sigma n from 0 to infinity 2 over 2n plus 1 times 1 to the 2n plus 1, which is 2 times sigma n from 0 to infinity 1 over 2n plus 1. Does this series converge or diverge? Yeah, Maggie in the chat is correct. Why does this series diverge? It's similar to the harmonic series, that's true. It's just the odd terms from the harmonic series, right? 1 plus 1/3 plus 1/5 plus 1/7 plus 1/9. So it's like exactly half of the harmonic series from a certain perspective. If we wanted to carefully argue that this is similar to the harmonic series, could I say that this is larger than the harmonic series and therefore diverges by direct comparison? Is 2n plus 1 bigger than 1 over n? Is 1 over 2n plus 1 this bigger than 1 over n? It's not, right? So what test would we need? Yeah, the inequality I would like to use for DCT doesn't work here. Yeah, so I would say this diverges by limit comparison with Bn equals 1 over n. And you can work out the details, right? You would take the limit of this 2n plus 1 divided by this 1 over n. That limit would come out to 1/2. And then you could say that the two series, sigma 1 over 2n plus 1 and sigma 1 over n, do the same thing. And since sigma 1 over n diverges, this series diverges. At the other endpoint, my series is sigma n from 0 to infinity 2 over 2n plus 1 times negative 1 to the, what's my power here? 2n plus 1. And since, just like before, this 2 can pop out, since 2n plus 1 is always negative, I'll write it out slowly here. Since 2n plus 1 is always odd, rather, this piece is always negative. This is just negative 1. So this is negative 2 times sigma n from 0 to infinity 1 over 2n plus 1. Well, this is just the negative of this series. This must also diverge. And you could say for the same reason, by LCT with Bn equals 1 over n. So this series diverges at both endpoints, thus the IOC is the open interval from -1 to 1. You can't include either endpoint. All right. Now, if you wanted to save yourself this work, the ratio test and the endpoint work, you could have done that also by making an observation about the two series that we combined to get this series. The two series that we combined both have half-open intervals of convergence. And when you add up two power series, the new interval of convergence will be the intersection, the overlap of the interval of convergence for the old guys. Let's take a quick look at that. I'll give just a second more for anybody who's writing here. let's make a quick observation. If we come back here, who remembers what the IOC is for this series? Oh, they're not even half open. Yeah, no, this is easier. Oh, no, they are half open. Yeah. So the IOC for this guy does anybody remember him? We cooked this up last time. I said we need to remember this series with its IOC. What was the IOC for the natural log of 1 plus x series? And look back at Monday's notes. It was -1 to 1. -1 was not included. +1 was. This series, which simplifies to this, has an IOC that is open on the right and closed on the left. The IOC here is also going to go from -1 to 1. But now if I plug in -1, I get a divergent series. Oh, let's see. -1 to 1, -1. Sorry, if I plug in -1, I get a convergent series. And if I plug in +1, I get a divergent series. So if you take the overlap between the two intervals of convergence here, what's common to both of these is just the open interval from -1 to 1. And you could have gotten the IOC that way as well. Okay. So this is my series. And the interval of convergence for this guy is the open interval from -1 to 1. Was there anything else from this last homework that you guys would like to take a closer look at before we talk about Taylor's theorem? Okay, then let's do it. Here's the idea. Suppose your function f of x has a power series centered at x equals a. So f of x can be written as sigma n from 0 to infinity Cn times x minus a to the n. I would like to find the coefficients Cn that make this the power series for this function. Right? The only part of the power series here that is unique to this function are the coefficients. Every series centered at A has this piece, and every power series has this piece. So it's the coefficients that actually make the series what it is. What we're about to do is discover a formula for the CNs. And then that formula will work for any function f of x. The first few terms of this series are C0, and then C1 times x minus a, and then C2 times x minus a squared, and then C3 times x minus a cubed, and so on. So my first step to find C0, I just go ahead and plug in a. Go ahead and plug in the center. That would be C0 plus C1 times a minus a plus C2 times a minus a squared plus C3 times a minus a cubed, and so on. What do you notice about this term, and this term? What can you tell me about these terms? They're all 0, right? A minus a is 0. A minus a squared is 0. A minus a cubed is 0. So this is just C0. In other words, you found the first coefficient. C0 is f of a. So if you want to expand some function as a power series, if you want to write a power series for a function centered at a, this very first guy is just f of a. All right. Now I differentiate my series. F primed of x. I'm going to differentiate this whole thing. The C0 is going to go away, and I'll get C1. The derivative of x minus a is just 1, plus C2, the derivative of x minus a squared is 2 times x minus a to the 1, plus C3 times the derivative of this piece is 3 times x minus a squared, plus the next term here would be C4 times 4x minus a cubed, and it goes on and on. That's the derivative of the series in the very first line. And now we're going to plug the center in here. So f primed of a is C1 times 1 plus C2 times 2 times a minus a plus C3 times 3 times a minus a squared plus C4 times 4 times a minus a cubed, and so on. And just like they were up here, these terms are all 0. So this is just C1, which implies C1 is f primed of a. So we've got our first two coefficients. If I want to go after the next coefficient, I differentiate again. F double primed of x. So now I'm differentiating this. This piece will differentiate to 0. This piece will differentiate to 0 plus C2 times 2 plus, when I differentiate this piece, I'll have C3 times 3, and then the derivative of x minus a squared is 2 times x minus a. When I differentiate this piece, I'll have C4 times 4 times 3 times x minus a squared. The next term would look like C5 times 5 times 4 times x minus a cubed, and it goes on. And again, if we plug in the center, you'll discover that f double primed of A is 0 plus C2 times 2 plus all of these, which are 0. In other words, C2 is f double primed of A over 2. And you can see how this is going to go. To get the next coefficient, I will differentiate the series again and then plug in the center again. So the third derivative of f, and this is where we change our notation, right? For 0 derivative, 1 derivative, 2 derivative, the prime notation works nice. But for higher derivatives, we use this notation. This is the third derivative of f, evaluated at A, or here I'll write it out, and then I'll plug in the A next. So this parentheses notation up here stands for the third derivative, because you don't want to write 10 primes for the 10th derivative. Your hand will get tired. All right, it looks silly on the page. So f3 of x, the third derivative of f, is what you get when you differentiate the second derivative. This piece will differentiate to 0 plus. Here I'll have c3 times 3 times 2 times the derivative of this is 1 plus. This piece, when I differentiate it, will become c4 times 4 times 3 times 2 times x minus a to the 1. This piece will become c5 times 5 times 4 times 3 times x minus a squared. And it'll continue on like that. So if you go plugging in a, the third derivative of f evaluated at a, this piece and this piece and all the higher order pieces will be 0. You get c3 times 3 times 2 times 1, which means c3 is f3 of a over 3 times 2 times 1. And you may start seeing a pattern here. We'll do one more. To go after the next guy, the fourth derivative of f. This will differentiate to 0 because it's a constant. This piece will differentiate to c4 times 4 times 3 times 2 times 1 times x minus a. To the 0, yeah, so this piece will go away. And then the c5 piece, this will be c5 times 5 times 4 times 3 times 2 times x minus a. The next term here would look like c6 times 6 times 5 times 4 times 3 times x minus a squared, and so on. So again, if you plug in the center, f4 of a, this will all be 0, this will be 0, all the higher order terms will be 0, so you get c4 times 4 times 3 times 2 times 1, which means that c4 is f4 of a over 4 times 3 times 2 times 1. So let me come back here and highlight the formulas we found for the coefficients so far. We have this guy for c4, this guy for c3, this guy for c2, this guy for c1, and this guy for c0. Does anybody think they see a formula in the CNs? There is a factorial, yeah. Yeah, the denominator is a factorial. And the numerator is the nth derivative of f of x evaluated at a. So here's the deal. Here's Taylor's formula. This says if f of x is equal to sigma n from 0 to infinity Cn times x minus a to the n, then Cn, the coefficient of x minus a to the n in this series expansion, is the nth derivative of f evaluated at the center divided by n factorial. In other words, you can write any function as sigma n from 0 to infinity fn of a over n factorial times x minus a to the n. That's it. So if you've got some function that you want to write as a power series, and you don't see any way to get there using the geometric series trick, then you can use Taylor's theorem. It's kind of mind-blowing, yeah. It absolutely is. Kind of the easiest way to think about this is as a generalization of the tangent line. Let's look at the partial sums. I'm going to call the partial sums of this series I'll call these guys Tn of x. T for Taylor. So instead of calling them Sn, I'll call them Tn. And then I write the x here to remind myself that they're functions of x. T0 of x, the 0th partial sum, the thing I get when I plug in 0 here, is f0 of a over 0 factorial times x minus a to the 0. That's just f of a. It's a constant. T1 of x is f0 of a over 0 factorial times x minus a to the 0 plus f1 of a over 1 factorial times x minus a to the 1. This piece right here is just f of a plus this piece right here, f1 of a, this is the first derivative of f evaluated at a, divided by 1 factorial, which is 1. This is f primed of a times x minus a. T2 would be f0 of a over 0 factorial times x minus a to the 0 plus f1 of a over 1 factorial times x minus a to the 1 plus f2 of a over 2 factorial times x minus a squared. That's f of a plus f primed of a times x minus a plus f double primed of a over 2 times x minus a squared. These are just the first few partial sums. Does anybody recognize T1? Think back to your Calc 1. What is this thing? You learned about this back in Calc 1. There's a few different names for it. L of x. Yeah, Batanji's got it. This is the linearization of f of x at a. In other words, it's the tangent line. So really what Tn is, the nth partial sum in the Taylor series, this first guy is a constant function that happens to agree with f at a. And this next guy is the tangent line or linearization to f of x at a. This guy is like the tangent parabola. Really what this formula here does, what Taylor's theorem does, is it gives you a series whose first n derivatives agree with f of x when you plug in a. And then it sends n to infinity. So the reason this series converges to this function is because it goes through the right point with the right slope and the right curvature. All of the derivatives of this series match all of the derivatives of this function at the center. That is the sort of intuition here. Tm here in general is called the nth Taylor polynomial for f of x centered at a. And it is the unique polynomial of degree n such that all of its derivatives up to n match the derivative of f of x. So I want to use this formula. I'm going to show you how to use this formula to get a few useful series that we don't have yet. The three big ones that we need are sine, cosine, and e to the x. I don't think we'll have time to do all of them today, but I'd like to get you at least the series for e to the x and kind of show you how to use this in general. Before I do that, a little preview. You don't have to write anything, just watch. All right. The blue line is T0. It's the unique constant function that matches the red at the center, which is 0. This guy is T1. He's the tangent line. T2 here is not the tangent line, But the tangent parabola, it's the unique quadratic function that goes through the point 0, 1, has the same first derivative as the red function at 0, 1, and the same second derivative as the red function at 0, 1. And you continue building up these polynomials whose first n derivatives match your function's first n derivatives at the center. That's how you get your Taylor series. Or at least that's geometrically what your Taylor series represents. How do I know to write 1 plus x, 1 plus x squared over 2, and so on? Well, I have that Taylor series memorized. Let me show you how to cook it up if you don't have it memorized. So, example. Find the Taylor series for f of x equals e to the x centered at a equals 0. A word about vocabulary, by the way. A Taylor series centered at 0 is called a Maclaurin series. Okay, just vocab. The name for a Taylor series where the center is 0 is the Maclaurin series. They mean the same thing. Remember that the formula here is that Cn is the nth derivative of f evaluated at the center, which here is 0, divided by n factorial. The way I like to do this is to make a little table. The Cn's go on the far right. The next thing over here is the nth derivative of f evaluated at the center. The next thing over here is just the nth derivative of x, because you need to calculate that if you're going to plug in n equals 0 or x equals 0. And then the far thing on the right here, I just put n. And we go ahead and say, all right, well, when n is 0, what is the 0th derivative of my function? If you differentiate e to the x 0 times, what do you get? Don't think too hard. But also, please don't leave me stranded here. If I take this function and I differentiate it 0 times, yeah, I get e to the x. Good. All right. Now, if I plug x equals 0 in here, f0 of 0, that's e to the 0. That's 1. Which means C0, you just take this guy and divide by n factorial. So that's 1 over 0 factorial, which, yeah, is 1. When n is equal to 1, f1 of x, the first derivative, if I differentiate e to the x once, I get e to the x. So f1 of 0, I plug in the center, is still e to the 0, which is still 1. So C1 is 1 over 1 factorial, which is still 1. If n is 2, the second derivative of my function, that's still e to the x. So f2 of 0, that's still e to the 0, which is still 1. So C2 is 1 over 2 factorial. I'll do just a couple more. When n is equal to 3, the third derivative of my function, No magic here, is still just e to the x. So f3 of 0 is still e to the 0, which is 1. So c3 is 1 divided by 3 factorial. And now if you jump down here to where n is just n, if you differentiate my function n times fn of x, you look for a pattern. Well, shit, here, this is not a hard pattern. It always just stays e to the x, which means fn of 0 is still always e to the 0, which is still 1, which means in general, Cn is just 1 over n factorial. This is how you use Taylor's theorem. You build this table, and you compute a few rows. Hopefully you notice a pattern. That pattern will allow you to eventually deduce what the nth row of this table looks like. The thing you're after is the bottom right element here, Cn. Thus, by Taylor's theorem, f of x, which is sigma n from 0 to infinity, Cn times x minus a to the n, is sigma n from 0 to infinity 1 over n factorial times x minus 0 to the n, right? A is 0. In other words, e to the x, which is f of x, is sigma n from 0 to infinity 1 over n factorial times x to the n. This is probably the most important power series in all of mathematics. The interval of convergence here, and you've actually done this as an exercise way back in 11.8, is negative infinity to infinity. And the first few partial sums of this series are exactly what you just saw me graphing. Let's come back and take a look at that. I'll give just 5 seconds for people who are writing. The first partial sum is just 1. The second partial sum is 1 plus x. The next partial sum is 1 plus x squared. The next partial sum after that, I'm writing y equals so we get the graph, 1 plus x squared over 2 plus x cubed over 3 factorial. Now would you look at that? Look how close this blue guy stays to the red guy, especially if you keep yourself near the center. He does a better job than the previous fella. And if you keep going, he will do better and better and better. The next partial sum looks like this, which does a little bit better job. So these are what Taylor polynomials look like as they converge. So what Taylor series look like. Again, T0 here is 1. T1 here is 1 plus x. T2 here is 1 plus x squared over 2. I'll write out a few more. T3 of x, 1 plus x squared over 2 plus x cubed over 3 factorial is 6. And in general here, Tn would be 1 plus x squared over 2 plus x cubed over 6, all the way out to x to the n over n factorial. It's the nth partial sum of this power series. If the Tn notation scares you, if you don't like this stuff, try to just hold on to your gut for a minute. Focus on finding this. Focus on being able to do the table and find the formula for the CNs and then plug the formula for the CNs into your series. That's the main skill. These things are just partial sums of this thing with a special notation. We call them T for Taylor. That's all. So your focus should be on finding series like this. All right. I don't think I have, much time. We did get started a few minutes late, so if you're willing to hang out for one, I can't force you to do that, can I? Okay, now then we're going to stop here for today. I will extend the current homework. We need the series for sine and cosine, the binomial series, before you can continue. So unfortunately, we lost a lot of time this week. There are plenty of problems you can do. So before you go, there's no reason to not finish all the way up through, let's see, you've got everything you need for 9, you've got everything you need for 10, definitely 11. Yeah, actually, I think you could do most of these. You could do 12 and 13. Nah, shit. Honestly, you can do all these now, up to 17. So 17 and on are relying on power series that we haven't cooked up yet. Actually, a few of these you could do, but I'll say that, right? So please try to complete up through problem 17, up through problem 16 by Monday. And then on Monday of next week, we will pick it up there. That will get you the power series for sine and cosine, and we'll get just a little bit more practice with these things. All right, so finish through 16, 1 through 16 in homework 11. I'll leave that open, and then we'll pick it up there on Monday, okay? Patanji, did you have a question?
Yeah, so I have a thought to find the interval about the homework.
I can't quite hear you. Could you hold the microphone a little bit closer?
Okay, I said that, do you hear me now?
That's a little bit better, yes.
Okay, I said that I have a talk to find the interval about the homework, I think 10.
I'm losing you again. Something about an integral, like this one or this one? So here you would write the inside as a series and then integrate. Right, so if you want to hang around, I'll take a look at how to do number 6 real quick. All right. I still can't really hear you very well, Antoine. I'm sorry. Could you maybe type into chat if this is not the problem we wanted to see? You too, Maggie. So I think the question was, how do I do problems like this? And I'm sorry if it wasn't, I couldn't quite hear you. How do I evaluate this as a series? First, you find a series for t over 1 minus t to the 9. Then you integrate that series. And we learned how to do that on Monday. The interval for homework 10, number 22. This is homework 11. 21, okay. So here we're getting everything from the geometric series trick. If you want to get, remember the trick to finding this series is to write it like this. And you factor out a 16. So this would be x squared over 16 times the sum from 0 to infinity, negative x to the 4 over 16 to the n, which is going to be sigma n from 0 to infinity, negative 1 to the n, times 1 over 16 to the n plus 1, times x to the 4n plus 2. I think we did this last week. There's two ways to find the IOC here. You can run the ratio test on this. Just treat it like any other power series. Run the ratio test. Or remember that you're using the geometric series trick with r equal to negative x to the 4 over 16. So the series converges if and only if the absolute value of r is strictly less than 1, which is the same as saying the absolute value of negative x to the 4 over 16 is strictly less than 1. So if you solve this inequality, that will give you your interval of convergence. This is the same. I'm going to skip a few steps here because we have to go quick. And then the fourth root of 16 is 2. And you could test the endpoints. You don't have to, because it's just a geometric series and you haven't done any integration or differentiation. So the IOC, you could say, is 1 of negative 2 to 2 like this, negative 2 to 2 like this, negative 2 to 2 like this, or negative 2 to 2 like this. Now, test the end points. And so at x equals negative 2, what do you get? And at x equals 2, what do you get? Does that make sense?
Yeah.
Okay, cool. So you know your IOC is one of these, and then you take both 2 and negative 2 and you plug them in for x here. If that series were to converge at both 2 and negative 2, then this would be your IOC. If that series were to diverge when you plug in both 2 and negative 2, then this would be your IOC. If this series were to converge when you plug in positive 2, but diverge when you plug in negative 2, this will be your IOC. All right?
Okay, my problem is about the interval, so I find out.
I'm sorry, I couldn't quite hear your comment there. What was the comment? Okay, cool. All right, then I will see you guys on Monday. Please try to complete up through problem 16 and homework 11, and we'll pick it up there next week. Take care.